So today we're going to be starting with 4.6, and we're basically looking at two types of reactions in this spread. We're looking at oxidation reactions and we're looking at combustion reactions. So that's basically what we're going to be looking at today. So oxidation reactions, as the name suggests, oxidation, they involve a reaction that basically involves oxygen, okay? You might have heard of the word oxides before. In fact, if you think back to your first practical you did, there was a question that was something like, if the guy had taken the steel wool and, what was the purpose of the experiment, taking the steel wool and rubbing the metals? And a lot of you mentioned that it was to remove oxides, okay? Generally, what happens with any metal is that when that metal comes into interaction or reaction with oxygen, it actually forms oxides on the surface. So what that means is that oxide is almost like an impurity, and we can't actually do any experiment or any test of reactivity when there are oxides on the surface of the metal, because as a lot of you mentioned in that answer, it affects the results of the experiment, okay? And it doesn't allow us to see the true reaction there. So that's what an oxidation reaction is. It's basically when an element reacts with, let me just admit these people in. It's usually when an element reacts with oxygen, okay? And there are multiple examples that we can talk about, okay, in everyday life. For example, if you've ever seen a building or some like construction area or any object that's made of metal, when it's been left out in, outside for a very long period of time, it actually starts to form something called rust, okay? In other words, it starts to corrode, okay? This process of corrosion is a direct effect of that oxidation reaction there. Okay, even something like the browning of an apple. If you cut an apple up, for example, and you tell yourself, okay, I'm going to just go do something and come back, your apple's going to start looking a little bit less fresh than it was when you first cut it. And that's because of that process of oxidation, which actually accelerates the process or the speed at which the apple kind of browns. Okay, so these are two examples of oxidation reactions that we see in everyday life. Okay, so that's the basic definition there. So if we look at the next slide, it's kind of a repetition of what we just went through with those two examples. But we also need to remember that when we have an oxidation reaction happening, what does that look like in terms of the formula? Okay, generally when we have a metal, could be any metal, could be magnesium, could be iron, whatever it is, plus oxygen gives us the metal oxide. Okay, here in this little picture here, the dark blue one, you can see that they've given you an example or a balanced equation example for magnesium, for magnesium oxide. Okay, so when magnesium, which is a metal, combines with oxygen, which we know is a non-metal, they basically form magnesium oxide. What they've done here is they've literally just balanced the equation out for you there. Okay, so that's the basic idea. So like I said before, oxidation of metal, one example that we can see is that we see that in corrosion, okay? And corrosion is very much related to that process of rusting that we see in a lot of the metals, particularly in iron. Okay, oxidation reactions are exothermic, which means that they produce energy in the form of heat. Okay, they don't absorb energy from the environment, but they produce energy in the form of heat and they relay that to the external environment. Now, the amount of heat that is produced depends upon the actual reactivity of the metals. We know some metals, for example, are more reactive. For example, our group 1 metals. Okay, looking back to chapter 3 now, can anyone tell me in the chat box, out of group 1 and group 2 metals, which one was more reactive, did we say? Yeah, excellent, group 1. So that means that we can probably expect a different amount of heat or a different kind of exothermic property to come out of an oxidation reaction when a group 1 metal is involved compared to when a group 2 metal is involved. And this may even be different for other metals like our transition metals, okay? So it really depends on what kind of metal we are dealing with in that situation or in that scenario. Okay, so that's basically just a little introduction into oxidation reaction and basically just the definition of what it is. Okay, you might also remember the term, metal oxide from when we did our acid metal reactions. Acid metal we did the second type of reaction we were focusing on in that spread in 4.4 was acid metal oxide reaction. So what happens when an acid, for example, hydrochloric acid, combines with you know, a metal oxide like magnesium oxide, for example. Okay, so we kind of came across a few examples of metal oxides when we did that as well. Okay, now when we're talking about oxidation reactions with non-metals, because so far we've only been looking at metals like iron, magnesium, group 1, group 2 transition metals, but what about our non-metals, okay? What happens there? Well, if you remember, one specific group of non-metals that we studied, which was the last group in our periodic table, group 18, were actually called the noble gases, okay? And the noble gases we said were completely stable, okay? They were completely stable. They already have a full outer shell because they've already got 8 electrons in their outermost shell for each one and 2 for helium. So basically what that means is that because they're fully stable, they don't need to go kind of like begging to other elements or to other metals to get those extra electrons that they need to become stable or to become complete. They're complete on their own. And that's why we kind of said they're a little bit snooty, a little bit kind of full of themselves, because they know that they don't need the common elements or the common folk to make them stable. So just like they don't interact, or just like the noble gases don't interact with other metals or non-metals, they also do not interact with oxygen as well. Okay. However, some of these noble gases can interact with, like for example, xenon. Okay, xenon is one example, and I think we talked about this when we did noble gases. Xenon can interact with other non-metals like fluorine, for example, under specific circumstances. Okay, what we're looking at now, and you might remember that when non-metals interact with one another, that's an example of a covalent bond. Okay, and the opposite is true for ionic bonding. In ionic bonding, it's a non-metal versus a metal. Okay, but covalent bonding is where we see a non-metal interacting with another non-metal. Okay, and these are 2 examples of those kinds of reactions. Okay, hydrogen and oxygen, they're both non-metals. They combine to form water. Carbon and oxygen, they're both non-metals. They combine to form carbon dioxide. So what I want you guys to do now, and these are really simple, so I think we can probably do them, is I want you guys to write down the chemical equations that represent these worded equations. And if you need to balance them out, make sure you balance them out as well. So what I'm going to do is I'm going to give you guys about 2 minutes, maybe 3 minutes. I'll put 3 minutes on the clock. Just see if you can come up with the balanced chemical equations for these 2 worded equations there. Okay, 3 minutes. So that's how we balance out those 2 equations there, okay, for those worded equations. So let's keep moving on. Okay, so when we're talking about combustion reactions are really important. And you might have heard of the word combustion with reference to things like energy production or lighting a fire. And those are all examples of how combustion is used in everyday life. For example, when we go and we turn on our stove, okay, or when we turn on the barbecue, that's an example of combustion. Okay, cooking. Another example of combustion is when you, you know, like when you're going camping and you're lighting a fire in the middle of the woods, that's an example of combustion as well. Okay, the process that your car uses to turn on its engine to burn the fuel to allow you to drive the car, that is another example of combustion. So there's so many examples of combustion that we use in our everyday life, and that without combustion, we wouldn't be able to really do the things that get us from point A to point B, or that allow us to basically live the lives that we do. Okay, combustion reactions are a bit different from all the other types of chemical reactions we've looked at so far in chapter 4, in the sense that they require oxygen and they require a fuel. Now, when we talk about fuels, the basis of most fuels, or the kind of like basic components or basic foundation of most of our fuels, whether that be crude oil, whether that be you know, whether that be coal, whether that be natural gas, is hydrocarbons. Okay, hydrocarbons are basically the basic foundation of your fuels, and they're literally just any compound or substance that's made up of carbon atoms and hydrogen atoms. Okay, and that's why we call them hydrocarbons. Okay, so the name itself gives it away. Hydrocarbons are one of the most common types of fuels that are used to produce energy. Okay, energy to require us to do all the different tasks that we just talked about, and all those examples. Now, a fuel is a substance, and this is how we define fuel. A fuel is a substance that will undergo a chemical reaction in which a very, very significant amount of useful energy is produced, and it's produced very rapidly, but it's not produced so rapidly that we can't control that. For example, when we light a fire or when we turn on the barbecue, we're still able to control that energy, okay? It doesn't get away from us, in other words. So a fuel is that kind of substance. So it's not just important for us to know that, oh yeah, examples of fuel are natural gas, coal, blah, blah, blah. It's also important for us to know the characteristics of what a fuel is, okay? And all fuels will show these similar characteristics or similar key features there. So that's basically just an introduction into what combustion reactions are. So just know that they require oxygen and a fuel. Now, when we're talking about combustion of hydrocarbons, as you can see here in this image, someone's kind of lit a fire there in the fireplace. That's an example of combustion of hydrocarbons. In order to light that fire up, you need oxygen and you need a fuel, okay? So you can't really light a fire in an area where there's no oxygen at all. It's not going to happen. It's not going to work, okay? Because oxygen is one of those requirements then. As you can see in this diagram here, in order for combustion to occur, you need oxygen coming in. Okay, and what's going out is heat. So heat, because again, it's an exothermic reaction. And then obviously you need fuel as well. So fuel and oxygen are required. They're the requirements. Heat is the kind of product that's going out into the environment. I don't know why these definitions are repeated from the previous slide, but yeah, that's just, again, just a repetition of what we just went through. Okay. So when we're looking at combustion, we can talk about two types of combustion, okay? We can talk about complete combustion and incomplete combustion. Complete combustion is when you need a complete supply, or we could say an excess or a plentiful supply of oxygen in order for the combustion reaction to occur, okay? So I need a complete supply of oxygen. When we look at complete combustion, the main products are carbon dioxide and water, okay? Water usually in the form of water vapor there. Okay, so when we've got methane plus oxygen, for example, combining together, we have the production of carbon dioxide and water. So those are always our products. They're kind of like constant to any combustion reaction there. Okay, this is just showing you the visual representation of what that looks like in terms of the atoms and the molecules that are involved there. And this is a balanced equation because we can see there are coefficients there. Okay, so they've just balanced that out. So that's basically what complete combustion is. So just remember, complete combustion requires a complete or a plentiful or a lot of oxygen in order to occur. Okay, you can't carry out complete combustion processes like lighting a fire in a room that's devoid of oxygen, that doesn't have oxygen at all. Okay, so that's the complete combustion. And we'll watch a video that differentiates this one and the next one as well. Okay, before we go to the next type of combustion, which is incomplete combustion, how many of you have heard of carbon monoxide poisoning before? Like you've heard of this term, or you've heard of this, maybe you've read about it in a book, or you've seen it in a TV show or movie. No? Okay. Well, I think I watch different TV shows than you guys. All right. Carbon monoxide it's a popular way that, I know this sounds thing, but it's a popular way that people kind of, it's poisonous. Obviously, carbon monoxide is a poisonous substance. It is facilitated through the process of incomplete combustion, which means that you're basically trying to create a fuel there or a product there in the absence of oxygen. So one of the most common examples of this that we see in a lot of popular culture is if someone wants to kill themselves, they kind of close their garage door, close all the doors, sit in their car, have the windows open, turn on the car, and they basically suffocate to death. The reason they suffocate to death isn't because of the smoke, it's because of the carbon monoxide that builds up in that environment. Okay, so this is why I said it's actually one of those things that's kind of well known in popular culture as a way that people kind of, and in books and stuff like that. Anyway, if we look at the actual science perspective of it, it is still poisonous, okay? It's poisonous because the substance itself is poisonous. That doesn't mean that you just need to be like, ready to kill yourself in order to be exposed to that thing. Actually, as one of you mentioned in the chat, it does come through things like kitchen appliances, through fireplaces, okay? And a lot of the time it's completely normal and safe if those appliances are properly, regulated and properly monitored. But if you have excessive exposure to carbon monoxide because of maybe a faulty appliance or because of some failure there in the appliance or some defect, that can actually lead to carbon monoxide kind of permeating throughout your house or throughout your home. And obviously, because you can't see it, because you can't smell it, you don't actually realize that that's actually affecting you until you start to develop symptoms that just come out of nowhere, like nausea, chest pain, irregular heartbeats, and all that stuff. As we're going to learn in the next slide, carbon monoxide is actually quite a thing to be concerned about, particularly because it actually attaches itself or binds itself to your hemoglobin in your red blood cells, and actually kind of starts to how would you say, concentrate in your blood and stop that proper blood flow there. Okay, so I just wanted to talk about this carbon monoxide poisoning because carbon monoxide is actually an example of incomplete combustion. And it's when you burn hydrocarbons in the absence or in the limited supply of oxygen. So incomplete means it's not complete. So we don't need a lot of oxygen in order to engage in the burning of hydrocarbons, okay, in incomplete combustion. You're still burning some kind of fuel, but you're doing so in a very limited supply of oxygen there. Okay, so that's the idea. So the products of incomplete combustion are carbon monoxide. Notice that that's different from complete combustion, where complete combustion had carbon dioxide as our product. Okay, and water is still product there, constant product. Okay, so the only difference between complete combustion and incomplete combustion is that in incomplete combustion you've got carbon monoxide as the product, whereas in complete combustion, the one we looked at before, you've got carbon dioxide. Now you might be thinking, okay, what's the difference between the two? Well, the difference is in the prefixes. Remember when we learned about the prefixes in chapter 3? What did we say mono stands for? What number, guys? And if anyone remembers, put it in the chat box. Yeah, 1, excellent. So mono means 1, and that's why the symbol for carbon monoxide is not CO2, it's actually CO, because we've only got one molecule there of the oxide, monoxide, meaning 1 oxygen molecule. Whereas in carbon dioxide, we said the D prefix means 2, or the di prefix means 2. So that's why we've got 2 in the symbol for carbon dioxide and only 1 for carbon monoxide. So that's basically the general template there that we've got. Okay, everything else stays more or less the same. It's just the carbon monoxide / carbon dioxide that's different for the two. Okay, and as I said in the previous slide, carbon monoxide is poisonous. It is toxic, okay, because it does bind or attach itself tightly to the hemoglobin in your red blood cells, even tighter than oxygen would bind. So what it does is it actually kind of causes a lot of issues like shortness of breath. It can even lead to death, okay? And one of the main concerns that people have is sometimes people have monoxide poisoning in their homes and they don't even know that they have it. But because of modern technology like carbon monoxide alarms and stuff that can detect the levels of that in the home, a lot of deaths have been prevented in recent years. But maybe 20, 30, 40 years back, before all these technology came into play, it was quite a concerning thing, okay? Alrighty, so okay, there's a question here. So combustion of carbon fuels require a well-ventilated environment. Can anyone give me a reason why? And it's very similar to what we just talked about now. Yeah, so yep, to protect you so you don't die. Yeah, correct. Okay, that is literally the basic simple answer there. Yeah, so we need to combust carbon fuels in a well-ventilated environment. Number one, so that we don't have a buildup of carbon monoxide in the case of incomplete combustion and we don't die. But also number two, because incomplete combustion, which is where we have a lot of the combustion of our carbon fuels, we need high levels of oxygen, and we don't have high levels of oxygen in a closed up environment. Okay, we need to have a well-ventilated environment. So just think about the example, guys. You're going on a camping trip, you've got to light a fire up in the middle of the forest. The reason that fire lights up so well is because you've got so much oxygen around you in that forest. It's an open space, it's open air. Okay, so that's why we are able to usually combust carbon fuels better in well-ventilated environments that have high levels of oxygen compared to kind of low. So better combustion occurs when we've got high levels of oxygen. And that's usually the case, high O2. And we usually see cases of having high oxygen levels in well-ventilated environments, okay, rather than closed off environments. This is particularly the case for complete combustion, where having high levels of oxygen is a complete requirement. Okay, cool. So that's basically the difference between incomplete and complete combustion. And look, you might be like, okay, if incomplete combustion is so dangerous for our health, why do we need it? Well, we need it because incomplete combustion is still important. For example, think about it. When we are not lighting a fire in the forest, but we're going inside and lighting a fire in the fireplace of our home, or we're lighting, we're turning on the stove or turning on the barbecue. That's sometimes in places that are not as well ventilated, okay? So sometimes we need to have incomplete combustion. And like we said before, carbon monoxide can be produced by home appliances as well. So it's not like we can completely give it up because we don't just all live outside 24 hours a day, okay? So we do have instances where we need to go back to our homes and we need to go back into a less ventilated environment there. Okay, the last two slides that we're looking at are about carbon fuels and the carbon economy. Basically talking about this idea that with carbon fuels, we are producing energy in the form of light and in the form of heat. So just think about the example of a fire. When someone lights a fire in a fireplace, that requires carbon fuel and hydrocarbons. And we usually see a lot of light coming up. For example, if you light a fire in a dark room, there's a lot of brightness that comes out of that. And there's a lot of heat that also emanates out of that as well. Okay, so we need that light and that heat and that fuel to basically power everything in our society. Everything in our society is dependent on carbon. Okay, even though we know carbon emissions are bad for the environment, the reason that they've come to this all-time high is because we've been so dependent on them and we've overused carbon for the for the past few decades. Okay, we need it so much, we can't do without it. So because our society runs on carbon, and because carbon is kind of like the backbone of our economy, it's the backbone of our society. We can't have a society or economy without carbon. That's what's known as a carbon economy. Okay, the fact that carbon is a very important fuel and that we need it for basically everything that we do with reference to normal functioning in our society. Okay, if we didn't have carbons, we wouldn't be able to, go and drive our car to work or drive to school. Public transport and things wouldn't run. Okay, we're still not completely hybrid in Australia, so we still don't have those alternative energy sources that are well established just yet. So we do depend on this a lot. Okay. Now, with carbon, even though we say carbon is, one component of the hydrocarbon that's really important for fuel, we can actually break down carbon and break down crude oil into different components or different functions through a process known as fractional distillation. Okay, so what fractional distillation is we take crude oil, which is what we see in the image here. We take crude oil and then we basically heat it up. And as we heat it up, different components or different fractions or different constituents of that crude oil and the hydrocarbons in that crude oil are basically collected. Okay, and we can actually reflect these in the fractional tower. So I'll show you guys all that on the next slide. That will make it more clear. So this is our fractional tower, or we can call it fractionating column. So basically what we see here is that depending on how much you heat your crude oil, to what temperature you heat it up, it can form different functions there. For example, when you heat up crude oil at a kind of low or relatively cool temperature, doesn't seem cool, but according to our fractional tower, it is cool. We get petrol. Okay, petrol is what we need to control our car, is what we need to run our cars and run our motor vehicles. Okay, it's important to maintain that temperature. If crude oil was to be heated up to, for example, this temperature, we wouldn't be able to put this in our car. We would be able to put it in a truck or a tractor or one of those kind of bigger cars that require diesel, but we wouldn't be able to put it into a normal car. Let's say you've got a Corolla or you've got a hatchback or you've got a sedan, one of those smaller cars, it wouldn't work. That's the reason why when you go to the petrol station, you have to be very careful to actually fill up your car with petrol and not diesel. Okay, if your car is running on petrol, because the fact that these two are different temperatures can actually affect the functioning of your car and maybe even permanently damage your car. okay, because your car's not meant to run that temperature or that kind of, that type of fuel there. You can see that there's a big difference or a big jump between those two. Okay, when we're talking about the rest of the examples here, you can see in the first one there, bottled gas is kind of the coolest one in terms of temperature. It is stored at less than 40 degrees. As we heat it up, it gets higher and higher. So you can see it goes from cool to high at the bottom. The highest fuel is what we see as residue. Residue is the kind of oil that's used for making bitumen. Bitumen is basically used for laying down our roads. It's used for a lot of roofing on industrial buildings and that kind of stuff. So you can see a lot of examples in between. Now, you're not required to learn these examples or learn these degrees amounts word to word, but it's just here for your understanding, to understand that we can take something like crude oil and we can heat it up to different temperatures, and that depending on the temperature that it is, it will form different properties. For example, when that crude oil is a bit cooler, these are the properties it has. It flows easily. Okay, if you've ever put petrol for your mum or dad's car, or you've seen them doing it, you'd notice that as soon as you click the button on that little petrol pump, it starts to flow. The petrol starts to flow into the car. Okay, so that's the basic idea. It also ignites easily, which is why people always like, don't use your mobile phones near, petrol stations. Don't, light a match or light a cigarette nearby, blah, 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 because it is quite volatile. As you can see, as we move further down the fractional tower, you can see that the crude oil starts to change in terms of its properties as it gets heated up. Okay, it starts to become not very volatile, which means it becomes easier to handle. It's not as unpredictable anymore, but it doesn't flow as easily. So lubricating oil, for example, fuel oil, you can't use these for example, fueling up a car, okay, because now they've got different properties and they've got different functions that make them no longer usable for that function, but make them usable for these functions. Okay, that's the basic idea behind the crude oil fractionating column there. Okay, so I think, yeah, that's basically it. So now we're just looking at the summary. So today what we've looked at is we've looked at oxidation reactions, basically defined as when an element reacts with oxygen, okay, and that produces metal oxides. So metal oxides are the main product that come out of that. So oxidation reactions is a metal reacting with oxygen to produce a metal oxide. Okay, metal oxides can take many shapes and forms. Some examples being the browning of an apple. Okay, if I can draw an apple, the browning of an apple, or the rusting or corrosion on a on a metal like iron, for example. Okay, all that kind of stuff are just examples. Combustion reactions were the second type of reaction that we looked at. So combustion reactions basically occur between nonmetals and oxygen. Okay, again, oxygen being a key component there. They produce large amounts of energy very quickly, but in a controllable way. And they produce energy in the form of heat and light. So remember the example of the fire burning. Okay, when fire burns or fire is ignited, or combusts, basically we see heat and light, and those are the two energy forms. The combustion of hydrocarbons, okay, produces water and carbon dioxide. This is what we call as complete combustion, okay? When carbon dioxide is there, that is complete. When carbon monoxide is the product though, that's what we call as an incomplete combustion, okay? So that's the difference between the two. And yeah, and like I said, complete combustion has carbon dioxide as one of the main products, whereas incomplete combustion has did I say monoxide? I meant to say complete combustion has carbon dioxide as one of the products. Incomplete combustion has carbon monoxide as one of the products there. Okay, everything else remains constant. So the water remains constant, the hydrocarbons remain constant, everything else is the same. All right, so hopefully that makes a bit of sense there. So what I'm going to do is I'm probably just going to stop the recording here.